Hey there, my lovelies in Keys Pre-Calculus. I am so sorry I cannot be there with you today, but I am running a fever and it would not be wise for me to be around you because I know that this is contagious. I got it from Robbie. Anyway, we're going to look at section 6.3 today, the last half of it. We're going to talk about unit vectors, linear combinations of unit vectors, and direction angles. I'm going to try to be as clear as I can on this. I'm going to have Mr. Pattison stop the video and let y'all practice some problems a couple of times, and hopefully this will help you with your assignment. Just like it is useful to have a unit circle for trigonometry where the radius is 1, it is also useful in many applications to have a unit vector whose magnitude is 1. So sometimes we don't really care about the magnitude, we just care about the direction of a vector. So we're going to learn to take any vector and rewrite it as a unit vector in that direction. And all you have to do to write a unit vector in the direction of vector v is to simply take that vector and divide it by its magnitude. So if you're given a vector in component form, or if you find the component form of a vector, all you have to do is take that component form and divide each part of it, the x direction and the y direction, by its magnitude, and you're going to get the unit vector. So we're going to take our vector v and we're going to write vector u as a unit vector in the direction of vector v by saying the component form of v divided by the magnitude of v, or you can also write it as 1 over the magnitude of vector v times vector v. So let's do an example so you understand what you're doing. So your instructions in example 4 say to find a unit vector in the direction of v and verify the result has a magnitude of 1. So the first thing we're going to do is find the magnitude of v, or the length of v, and we do that by taking the square root of the v1 squared plus v2 squared. So v1 is negative 2, so I'm going to say negative 2 squared, v2 is 5, so 5 squared, and I get the magnitude of v is equal to the square root of 4 plus 25, which is the square root of 29. And this is in its simplest form. There are no perfect squares in 29. So, now that we have that, we can take 1 over the square root of 29 and we can multiply it by each component of the vector v. So, my unit vector is going to be equal to negative 2 over the square root of 29 and 5 over the square root of 29. This is not in its simplest form. You can simplify it to negative 2 square roots of 29 over 29 and 5 square roots of 29 over 29. That is the simplest form. However, it's not as easy to work with the simplified form as it is to work with this first form right here when you're trying to find the magnitude of this new unit vector. So we're going to verify the magnitude of the unit vector u that is going in the direction of vector v to be 1. So we're going to use the part that I underlined to verify its magnitude. So the way I would do that is I would say u, the magnitude of u is the square root of negative 2 over the square root of 29 squared plus 5 over the square root of 29. That's the whole thing squared. So negative 2 square root of 29 squared is 4 over 29 squared plus 5 over the square root of 29 squared is 25 over 29. And when I add those together, because they have common denominators, I get 29 over 29. So the square root of 29 over 29 is the square root of 1. which is equal, in fact, to magnitude of 1. We're just taking a positive because we're talking about a length. Now, I would like for you to pause the video and try the problem on page 418, problem number 28. Pause the video, work out the problem, and then come back and we'll work it together. Okay, here's problem number 28 on page 418 worked out. You may want to pause the video again and double check your work. I added the extra step of verifying that the unit vector u was actually had a magnitude of 1. They did not ask you to do that on the homework, but I did it just to show you that it does work. So as you can see, finding unit vectors is fairly simple, and it's useful when we don't really care about the magnitude of a vector. What we care about is its direction. We're now going to talk about a couple of standard unit vectors. Okay, so last week we talked about vectors in their component form. That means same direction, same magnitude, but their initial point is at the origin, 0, 0. And then today we talked about unit vectors, where it's going to be the same direction, but our magnitude is 1. But now we're going to talk about a vector v that is maybe not a unit vector, but still want to write it in a standard form. So what I'm going to do is I'm going to look at a couple of standard unit vectors. One is the unit vector I that is parallel to or is along the x-axis. That's the horizontal vector with a magnitude of 1. So it would end, its terminal point would be the point 1, 0. And the vector j. It's a standard vertical unit vector, whose initial point is at the origin and its terminal point is at the point 0, 1. It's in the vertical direction along the y-axis. Now, I do want you to note that the letter I is a lowercase bold letter I. It is not cursive because the cursive I is the imaginary unit for complex numbers. The bold I, that is lowercase, is a standard horizontal unit vector. You can also represent it with a hat if you want to distinguish between the two, but you don't need to. Your book does not do it. You do not need to do it unless you want to. But the idea is that you can rewrite the vector v into a linear combination of the horizontal and vertical components of v. In other words, a linear combination of the vectors I and j. Remember, the component form of vector v is v1, v2. Okay? Now, if I want to write it as a linear combination, including or with the standard horizontal and vertical unit vectors, I can rewrite it as v equals v times the horizontal unit vector plus v2 times the standard vertical unit vector, 0, 1. Okay? v1 and v2 become scalars to those standard horizontal and vertical unit vectors. In other words, I can multiply v1 times 1, 0, and I would just get v1. And I could multiply v2 times 0, 1, and just get v2. And if you go back to the vector operation of addition, then you can see that I could take the v1 and add it to, or the I, and add it to the j, those two multiplied by the scalar v1 and v2, and I would get my vector v. Because I would take this one right here, and I would take the vertical, and I would start it here on the on its terminal side, and I would come back up, and I would get to v. All right, so that's why that works. But I can rewrite this a little simpler by saying this is the same thing as saying v1 times I I've just replaced the unit vector 1, 0 with the letter I, plus v2 times j. Those standard unit vectors. So v can be rewritten as vi plus v2. That is writing a vector as a linear combination of unit vectors. So let's do example 5 in your book, which is an example of how to do this with numbers. Okay, on page 413, it says, let u be a vector with initial point 2, -5, and terminal point -1, 3. Write u as a linear combination in the standard, linear combination of the standard unit vectors I and j. So I have drawn the problem up here. The first thing we're going to do is we're going to write u in its component form. And remember, we do that by taking the terminal x value, and we subtract the initial x value as our first component. And then we're going to take the terminal y value, and we're going to subtract the initial y value. And that's going to give our vector u in component form. So when I do that, I get u is equal, the component form of u is equal to -3, 8. And then when I want to write it as a linear combination of the unit vectors, all I do is rewrite it as -3 times I. Whoops, wrong I, sorry. Let me correct that. Plus 8 times j. Well, I wanted it to be blue. Hold on. And that is all you do. That's how you can rewrite the vector u into a linear combination of unit vectors. Now I would like for you to try page 418, number 42, and page 418, number 48. Pause the video, work on it, and when you come back, I will have the solutions up here for you. Okay, so here are the two solutions worked out. Pause the video, study them. I will talk about number 48 in a minute. The instruction for number 48 said to find the component form of v and sketch the specified vector operations geometrically, where u equals 2i minus j and w equals i plus 2j. Now, the component form is this form, -1, 3 right here. It does not include the I and the J. So you solve it with the I and the J, and it does make it easier to solve, so you can get like terms together. It really keeps things straight for you, but you write it without the I and the J, and so you're not adding those parts. You are writing it as a vector, a component vector, -1, 3. So the component vector, -1, 3, is this vector v right here. Negative u, which is 2i minus j, which it would be, positive u would be positive 2, negative j, but because it's the opposite of it, when v is equal to -u plus w, it's going to be going the opposite direction. So that's negative u, that's this little vector down here. I don't know if you can see that I'm, well, let's see. I don't know if the yellow is showing up or not. That's this one. And then w is 1i plus 2j, which is this one. And when I add those two together, if I take negative u, and I take the w, and I put it over there, the initial side to the terminal side of negative u, and make my w go up like this, I get the component vector. Now we're going to talk about direction angles. I'm going to try to go slowly. I'm going to try. So y'all can follow what doing here. This is on page 414 in your book. I've just recreated the picture here, and I'm going to read through what they say and try to explain what it means. Okay, if U is a unit vector, so I've got this pink unit vector here. I don't know if you can see the yellow circle, but this pink unit vector in the picture, U, or in the graph, U, theta is, the angle theta is measured by going from the x-axis counterclockwise up. Okay? It's from the positive x-axis to U. The terminal point of U lies on the unit circle, so U would be 1. This is a unit vector. Then you're going to have U equals the point, or the vector U, the unit vector, is x, y, which is really the same thing as saying cosine theta, sine theta. But if you wanted to write it as a linear combination of the two standard unit vectors, then it could be cosine theta I plus sine theta j. So that's that first line here. Okay? Now, the angle theta is the direction angle of the vector u. And remember, u is a unit vector. That means it's got the length of a magnitude of 1. But vector v can be any vector. That means it's going to have a magnitude that is different than 1. I mean, it could have a magnitude of 1, but it's not necessarily a unit vector. It's just any vector. And we're going to represent vector v as the linear combination of a times I plus b times j. Okay, this is any vector, and it makes the angle theta with the positive x-axis in the same direction as u. Therefore, you can rewrite v as the magnitude of v as a scalar times the unit vector cosine theta sine theta. So basically, all it's doing is just taking the magnitude of v and it's multiplying it by the unit vector cosine theta sine theta to get the magnitude you need. But you could also rewrite it as a linear combination of the magnitude of v times cosine theta I plus the magnitude of v sine theta j. Now I want you to notice that A basically is equivalent to magnitude of v cosine theta. And B, right here, is equivalent to the magnitude of vector v times sine theta. So I could substitute those in for each other in either direction. A is magnitude of v cosine theta, magnitude of v cosine theta is A, and the same thing for B and sine theta. Now we know that tan theta is the same thing by the quotient property, same thing as sine theta divided by cosine theta. So if I were to find the direction angle theta, I would use tan theta. And here I could multiply both the numerator and the denominator by the same thing. So I'm going to multiply both the numerator and the denominator by the magnitude of v. Now, remember that sine theta is equivalent to b, or excuse me, the magnitude of v times sine theta is equivalent to b, and the magnitude of v times cosine theta is equivalent to a. So you could say that tan theta is equal to b over a, and we are going to use that to find the directional angle of our vectors. I'm sorry if you're hearing noise in the background. My family is being loud. Okay, we're going to look at example 7 now. Example 7 says to find the direction angle of each vector. And part A, the vector u, is the written in its linear combination form. It's u equals 3i plus 3j. If I were to write it in its component form, it would be the vector 3, 3. You always want to draw your vectors when you're trying to find the direction angle.
The reason why you want to do this is because it matters what quadrant it lies in, but you're not always going to get the correct answer on your calculator. The reason you're not going to get the correct answer on your calculator is the calculator is programmed to give you the tangent or the arctan in quadrants 1 and 4. And if it's going to give you the arctan in quadrant 4, it's going to make it a negative number. It's going to go in this direction. But we're looking for direction angles. They've got to go in the counterclockwise direction. And all of your vectors may not lie in the first or fourth quadrant. So you always need to draw it, and then from there, we'll figure out what the actual answer is, what the actual angle is. So I'm going to draw this vector at 3, 3, which is about up here. And I can already tell you what the angle is, and you can probably see it too. All right, so here's my vector, vector u, and it's got its terminal side. If it's a component vector, its terminal side is the 0.33, its initial side is 0, 0. Now, I want to know what theta is. Now, it's already in the first quadrant, so I know that when I figure this out, I don't have to do anything extra. Theta is in the first quadrant, and that will work. So what I'm going to do is I'm going to say tan of theta equals a over b. Excuse me, I said that backwards. B over a. And my b here is 3. And my a here is 3. So tangent of theta is 3 over 3, which is equivalent to 1. So what angle theta gives me a tangent of 1? Well, if I do on my calculator, I would say arctan 1 equals, and make sure it's in degrees, and it would give you 45 degrees. Or if you know, you use your unit circle, and you should already also have it memorized, the tangent of 45 degrees is 1. So the arctan of 1 would be 45 degrees. And that's as far as you need to go on example A. There's nothing else to do because it's already in quadrant 1. Part B says vector v is equal to 3i minus 4j. If I were to write it in a component form, it would be 3, negative 4. And I did correct my I and j up here. I wrote them wrong. I wrote them in cursive, and they don't need to be. But over here, I'm going to write 3, negative 4, which is going to be in the fourth quadrant down here. 3, negative 4. So I know that when I do my arctan, it's going to give me a negative number because it's going to want to go in this direction, but I don't want it to go in that direction. I need theta. Let me erase this real quick. I need theta to go here in the counterclockwise direction, and it's a very large angle. Okay, so I'm going to have to do some figuring here, and that's why you always want to draw it. Now first part's fairly simple, straightforward. Tangent of theta is b over a. Well, b is negative 4, a is 3, and if you were to type this in on your calculator, arctan, make sure it's in degree form, arctan negative 4 thirds, you're going to get theta, or I shouldn't put an equal sign there, sorry. Let's see. You're going to get theta equals negative 53.13 degrees when you type that in on your calculator. Now, negative 53.13 degrees is this angle from the x-axis down to vector v. We don't want that angle. We want the clockwise angle starting at x and going, excuse me, not clockwise, counterclockwise. We want to start at the x-axis in the positive direction, and we want to go around to counterclockwise to theta being here. So how do I figure that out? Well, the whole thing is 360 degrees, right? And if I've used up negative 53.13 degrees going this way, then can't I just say that theta is also equivalent to 360 degrees? We can think of these as reference angles too. Minus 53.13 degrees. And when I multiply that out, or not multiply, when I subtract that out, I get 306.87 degrees as the correct directional angle, or direction angle for vector v. Now, I'm not going to keep going with this because we're running out of time. So y'all can study examples 8, 9, and 10. They're the application problems. I don't think I'm going to have any application for your homework right now, though. But you can watch this video again at home. You can practice these problems. They should be fairly straightforward when you do the homework. And I will expect it to be done on Thursday. I hope y'all have a great day, and I will see you later. Hopefully on Thursday.